This video we're going to look at finding the roots of complex equations. So we're going to look at quadratic equations and cubic equations and maybe beyond that as well. So for real numbers a, b, and c, so if you've got a, z squared plus b, z plus c, so this is a quadratic equation. And if there are non-complex numbers, so if a, b, and c are non-complex numbers, then the roots of this will, if their roots are complex, then they will appear in complex conjugate pairs. So if you know one of the roots, so for example, we'll look at this one. If you knew this was a root, 7 plus 2i is a root, then you know another one of the roots is going to be 7 minus 2i. So that's going to be make life very easy for you. Okay, so if you knew the roots, one of the roots of a complex number was alpha, and you knew another one was beta, then you could write the complex equation as z minus alpha is equal to z minus beta. Right, where this comes from, if you knew, if you had x minus 4 upon x minus 5 is equal to 0, then the roots of that equation are x equals 4 and x equals 5. So then if you expand this, what you would get is x squared minus 9x plus 20 is equal to 0. So we're sort of working backwards. So you're told what the roots are, alpha and beta. Then you can write the equation as z minus alpha, z minus beta, and then you would multiply that thing out to see what you get. So we're going to look at this example and see how we get on in it. Okay, so hopefully this makes a bit more sense when we get on to an example. So in this question, it says, given that alpha is equal to 7 plus 2i is one of the roots of a quadratic equation with real coefficients, state the values of the other root. So they occur in beta is equal to 7 minus 2i as, we'll just say, as roots occur in conjugate pairs. Okay. Part B, what part B says? It says find the quadratic equation. So we're just going to write z minus alpha upon z minus beta equals 0. So like the wee example I did there with alpha and beta equal to just completely real numbers. I think we're 4 and 5. Same idea here. So all we're going to do is fill this in. Just get down the page a wee bit. So we're just going to fill this in and then we're going to expand the bracket. So we have z minus, my alpha was 7. So I'll put it in the bracket 7 plus 2i. And my beta was then 7 and then minus 7 minus 2i. And we're going to multiply this thing out and see what you get. Okay, so the z times the z is easy, it's z squared. Then you've got z times the 7 times minus 2i, and that's times z. And then you've got minus 7 plus 2i times your z, and then you've got plus, and that's going to be 7 plus 2i upon 7 minus 2i. So it's not pretty at all, but we can work with it, we can get through. So this first term was just z squared. The next thing you're going to have is then minus 7z. Then you're going to have plus 2iz. Over here you're going to have minus 7z. Then you're going to have minus 2iz. And you can see these terms are going to cancel out to make life a wee bit easier. Over here, this last term, this thing here, is the difference of two squares. So it's just going to be 7 squared and minus 2i all squared. So that's going to be 7 minus 4 times minus 1, which is going to be plus 4, is equal to 0. Okay, tidy that mess up and see what you're going to get. You're going to get z squared and minus 14z, and then plus, oh, we're missing something. Oh, sorry, 7 times 7. I forgot what 7 times 7 is. 7 times 7 is 49. Very stupid mistake there. So that was 7 times 7 is 49. So then when we tidy that up, you're going to have z squared minus 14z plus 53 is equal to 0. Okay, part C of this question says find the values of alpha plus beta. So if you do alpha plus beta, that's just going to be 7 plus your 2i plus 7 minus your 2i, which just equals, that's an I, believe it or not, that just equals 14. And then you have to find alpha, beta. Now we've got this in your notes from earlier on, but we'll just go through it again. Alpha, beta is just going to be 7 plus 2i times 7 minus 2i. And if you do that out, that's just going to be 49 minus 4 times a minus 1. So 49 plus 4, which is going to be 53. Okay, again, we have this in our notes earlier on, but just to put it in again, just so we note, if z is equal to a plus ib, then z times its conjugate, complex conjugate, is a squared plus b squared. Okay, this one is a cubic example. It says, given that minus 1 is a root of the equation, z cubed minus z squared plus 3z plus k equals 0, find the value of k. So first of all, it says that minus 1 is a root, so just say if z equals minus 1 is a root. That means that if you put minus 1 through the equation, so minus 1 cubed minus 1 squared plus 3 times minus 1 plus k, it will be equal to 0. It will satisfy the equation. So that just works out as minus 1 minus 1 minus 1 minus 3 plus k is equal to 0, which means k is equal to 5. Okay, part B says find the other two roots of the equation. Okay, first thing I'm going to do is going to rewrite the equation as z cubed minus z squared plus 3z plus 5 equals 0. So I know that is what my equation is now. And we know that minus 1 is a root, which means, so just say if z equals minus 1 is a root, then what that means z plus 1. So how I've got that was z minus 1. So z plus 1 is a factor. Okay, what I intend to do now then is I want to just divide my z cubed minus z squared plus 3z plus 5 by z plus 1, and that will reduce it down to a quadratic, which I will possibly be able to factorize. We'll see. Okay. Right, I'm just going to pause the video and I'm going to write out this wee division sum. Okay, so as I said, this is my polynomial. I'm going to divide it by z plus 1. Notice here, very important, I've got my cubic term, my quadratic, my linear term, my numerical term. If any one of these be missing, so say for example I was missing my quadratic term, you must remember to leave the gap where it would have been. So it must be cubic, quadratic, linear, numerical, and you've got to have, if there's a missing one, you've got to leave a space where it would have been. Okay, we're going to get started doing this. So to do this, we're going to say how many times, or z divides into z cubed. So what do you need to multiply z? What do you need to multiply z by to give you z cubed? And the answer is z squared. So you line that up above your quadratic terms, and then you multiply z squared times this whole thing, which will give you z cubed plus z squared. And just do a line here. Some people put a minus in here. I don't like to put a minus because it confuses what sign this thing is. But what you are doing here is you're subtracting this line away from this line. So you have minus z squared minus another z squared, which is just going to be minus 2 z squared, and z cubed minus z cubed. Okay, if there's another term here, you bring it down. So this plus 3z comes on down. So plus 3z. And now what I'm thinking is, what I multiply my z by to give me minus 2z squared. And the answer is minus 2z. And again, that lines up with the linear terms. So now you're doing minus 2z times this whole thing, which will give you minus 2z squared minus 2z. And again, you're subtracting. So 3z minus 2z will just give you 5z. And the minus 2z minus 2z gives you 0. And then you bring this 5 down as well. So the 5 comes down. So there we have it. And now you're thinking, what do you need to multiply z by to give you 5z? And the answer is 5. So it's 5. And then when you multiply the 5 times the z plus 1, you get 5z plus 5. And when you subtract you get 0. This is what we were hoping to get in this question, because we wanted it to factorize as factorized completely. So what we have shown, therefore, that z cubed minus z squared plus 3z plus 5, it's equal to z plus 1 upon z squared minus 2z plus 5. That's what it's equal to so far. So we've already solved this bit of it. We already know the solution of this bit. The root of this bit is z equals minus 1. We want to find what the roots of this bit are over here. So I'll just say solving z squared minus 2z plus 5, and just jump to your quadratic formula. Z is going to be equal to 2 plus or minus brackets minus 2 squared minus 4 times the 1 times the 5, square root of all that, all divided by 2a, which is 2, and that works out to be z. And I'll just tidy this up for a bit of speed here. At z plus or minus root of minus 16 all over 2, which is the same as just 2 plus or minus, and that's going to be 4i all over 2. So z in this case is I plus or minus 2i. So we'll just go over here and just say our answer. The roots are z equals minus 1. We were told that one, I think, earlier on. And then we have 1 plus 2i, and we also have 1 minus 2i. And there's your 3 roots, and that's it done. Okay, and this example says, given that 3 plus I is a root of the quadratic equation, 2z to the power 4 minus 3z cubed minus 39z squared plus 120z minus 50 is equal to 0, solve the equation completely. Okay, now this is important. This is one of the roots. It says in your notes earlier on that roots will appear in complex conjugate pairs. So roots appear in complex conjugate pairs. So we'll just say if 3 plus I is a root, then 3 minus I is also a root, okay, because they appear in complex conjugate pairs. So that means z minus, I'll put that in a bracket, minus 3 plus I is a factor, and also z minus 3 minus I is a factor. So that whole thing combined is an even bigger factor, I suppose, is a factor of 2z to the 4 minus 3z cubed minus 39z squared plus 120z minus 50 is equal to 0. Okay, so we've got all of that. Okay, right. What we want to do then is multiply this thing out. If you multiply this thing out, you're going to get a quadratic, and then we can divide this, whatever this quadratic is, we can divide it into this thing. So this is a quartic, and that will reduce this quartic to the product of two quadratics, and then hopefully we can factorize all of those quadratics as well. So that is our plan. So we'll get started doing that now. So first thing I'll do is multiply this thing out and see what I get. Okay, the speed of 3 I've multiplied this out, the two factors, and I've shown most of my working out for this. So this was z times z, this was z times the minus of 3 minus I, and this was z times the minus of 3 plus I, and this was our minus of 3 plus I upon minus of 3 plus I. So you've got 3 plus I upon 3 minus I, which is the difference of two squares, so 3 squared minus I squared, so that's going to be 3 squared minus 1, which is 9 plus 1. So it tidies up to be z squared plus 6z plus 10. What we then want to do is divide that into the original quartic and see what we get. So again, I'm going to pause the video and I'll just do that out to save us a bit of time. Okay, so I've just divided my quartic by the z squared minus 6z plus 10. Again, just make sure there are no missing terms here. So if there's any gaps, if there's a cubic term missing, for example, you must leave the gap for it. And then first of all, z squared went into z to the power 2z to the power 4, 2z squared times, so multiply 2z squared times this. That's how I got this line here. Then subtract to get this line. Remember to bring down your next term. Then you're thinking, what do you need to multiply z squared by to give you 9z cubed? The answer is 9z. You do 9z times the whole divider, and that gives you this. And then you subtract, and it gives you minus 5z squared plus 30z. And then bring down to minus 50. And you think, what do I need to multiply my z squared by to give you minus 5z squared? And the answer is minus 5. So minus 5 times the whole divider gives you minus 5z squared plus 30z minus 50. And then subtract and you get 0. So if you don't get 0, you know you're on the wrong, you've done something wrong, so go back and check it. Very, very easy to get a sign wrong, especially when you're subtracting the likes of this. Minus 3z cubed, minus 12z squared, z cubed, and so on. A lot of people make mistakes and that sort of thing. Just take a wee bit of care. If you need to, do it in your calculator, hit in minus 3 minus 12, and it'll give you plus 9. So just check it if you need to, especially in the heat of an exam, when you're a bit nervous and so on. Okay, our quartic then becomes, we've got this quadratic times this quadratic gave you this quartic. So our quartic now becomes a quadratic upon a quadratic. And we then want to solve this one. This one, I think we already know. So we want to have a go at solving this one here. Okay, so I'm just going to write down the first bracket again. And the second one then we can factorize. My sum is equal to 9. My product is equal to minus 10. So my two numbers are going to be 10 and minus 1. So minus z minus 5. And I'm just going to go through and factorize this. So I'm just going to show all my working out here. I could have isolated this thing and done this over on the side and then brought it all together at the end. Might have been a more efficient way of doing it, but for all the time it will take me to do it this way. So I'm going to have 2z upon z plus 5 and minus 1 upon z plus 5 is equal to 0. And then there we have it. We have factorized this thing already. So that's going to be 2z minus 1 upon z plus 5 is equal to 0. So my roots are as follows. So we already had the roots of this thing earlier on. The roots of this were 3i. They weren't at all. That's nonsense. This won't rub out for some reason. The roots are going to be 3 plus I. And it was 3 minus I. Remember, that was the one that occurred in the complex conjugate pair. The roots then of these two, this one will have a root of minus 5, and this other one then, this one here, will have a root of 1/2, and that's it. So 4 roots, and you'd imagine a quartic generally will have 4 roots, unless it will have repeated roots. Okay. Okay, last example for this video, it says that show that z squared plus 4 is a factor of z to the power 4 minus 2z cubed plus 21z squared minus 8z plus 68. And it says hence solve. So first thing I'm going to do is just going to divide, and I'm going to show the working out this one, go through this one for you. I'm going to divide my polynomial by the z squared plus the 4. So I'm showing this one because it's a wee bit tricky, just because in my divider there is a missing term. So if you have a look in my divider, it's z squared plus 4, so we skip out the linear term. So you've got to leave a gap when you're doing the divider bit, which is the bit that's a bit awkward here. Okay, so first thing, z squared needs to be multiplied by what to give you z to the power 4? The answer is z squared. So you put a quadratic term here, z squared. Then you multiply your divider by z squared, so it gives you z to the power 4, and then plus 4z squared. So notice I've left my gap. Here is where I've left my gap. You then put a line underneath this and subtract. So 21z squared minus 4 is going to give you 17z squared. And this is a bit people get confused about. You have minus 2z squared and it's minus 8. Nothing's been taken away from it, so it just leaves you the minus 2z cubes, I should say, and then plus the 17z squared, and then z to the power 4 minus z to the power 4, it just disappears. You then need to bring down your next term. So bring down your next term, which was minus 8z. you're then saying z squared needs to be multiplied by what to give you minus 2z cubed? And the answer is minus 2z. So multiply your divider by the minus 2z, and that'll give you minus 2z cubed. And then it will give you minus 8z. And again, subtract. The minus 8z minus 8z, it disappears. And this term will disappear, so you're just being left with the 17z squared. And then bring this term down, which was plus 68. And then z squared needs to be multiplied by 17 to give you the 17z squared. So this is me multiplying my z squared plus 4 by 17. You get 68. And I have run out of space. I will just subtract those, and you get 0. So we've said so. That means z to the power 4 plus 4 is a factor. Okay. What we have to do says hence solve the equation. So we're just going to say rewrite, and we'll call it the polynomial, as z to the power 4 plus 4, put that in a bracket, upon z squared minus 2z plus 17 is equal to 0. So we want to rewrite that, and then what we want to do is we're going to solve both of these things. So first of all, z to the power 4, that wasn't a z to the power 4 at all, that was a z to the power 2. That was z to the power 2 plus 4, so z to the power 2 plus 4 is equal to 0, solving the first one, which means z squared is equal to minus 4, which means z is equal to plus or minus the square root of minus 4, which we can now do using our complex numbers. So that's going to be plus or minus the square root of 4 times the square root of minus 1. So z is equal to, that's going to be plus or minus 2i. Okay, I made a bit of a meal of that one, but we got there in the end. And this one, we're going to put z squared minus 2z plus 17 equals 0. And I'm going to jump to my quadratic formula just straight to it to do this one. Z is going to be equal to, z is equal to 2 plus or minus, brackets minus 2 squared minus 4 times my 1 times my 17, square root of all that whole thing, I should say, all divided by the 2. That was my 2a, remember? So that's 2 plus or minus. And if you do this out on your calculator, you're going to get minus 64, all divided by 2. So z is equal to 2 plus or minus, and that's going to be 8i over 2. So z is equal to 1 plus or minus 4i. Okay, just to have a wee look. This, one of my complex numbers, one of my roots is 1 plus 4i, the other one is 1 minus 4i, so it occurs in complex pairs. And this one, I suppose you could say that 0 plus 2i and 0 minus 2i, so again, it occurs in complex pairs. So we have a quartic, and the roots have been 2 sets of complex conjugate pairs. So your final thing, just say your answer. Roots are, we had minus 2i, we had positive 2i, we had 1 minus 4i, and we had 1 plus 4i, and that is you done for this video. Okay, you are now ready to do the following questions. Exercise B, questions 18 to 22.